Hey guys, Mr. Butts here. I want to talk about a really important type of problem that we can solve using differential equations, and that is an exponential growth or as exponential decay problem. So most of what we're going to do with this is actually going to be pre-calculus type stuff. It's just going to be algebraic manipulation with exponential equations and natural logs and stuff like that. But the reason that we can do all of that pre-calculus algebraic stuff comes from a solution to a differential equation. So let's first talk about what kinds of situations we can use this. There are a lot of situations in the world that fit this description. So the rate of change of some quantity is proportional to the quantity itself. So some examples of this would be like interest on a loan. So if you're earning or paying, I should say, if it's interest on a loan, if you're paying 3% interest, that means that the amount that you actually pay on the loan is going to be proportional to the amount that you owe on the loan. So 3% interest, if you only owe $100, then you owe $3. But if you double the amount that you owe, then the interest is also going to double. Population growth is the same thing, or at least it can be in certain conditions. So if you're looking at how fast human population or bacteria population or whatever, some population is growing under ideal conditions, it can grow exponentially. So a population of 10,000 can grow at a certain rate. A population of 20,000 that is twice as big could grow twice as fast. So population growth can fit this under ideal conditions. Radioactive decay is another one. So you may be familiar with the idea of carbon dating. And the idea of carbon dating is that the amount of carbon 14 that decays into carbon 12 is predictable, and the amount that actually decays over some time period is proportional to the amount of carbon 14 in the sample. So that fits this description. If you have a cup of coffee or hot chocolate or really anything that isn't room temperature, so it doesn't even have to be a drink, but it could be really anything. It's going to tend toward the temperature of the room, room temperature, the surrounding temperature. So if we think about the temperature of a cup of coffee, if it starts out at 150 degrees and the room is 70 degrees, the temperature of the coffee is going to get closer and closer to that. And that's actually going to be at a rate proportional to the difference between those two temperatures. So if the coffee is 150 degrees and the room is 70 degrees, then it's going to be cooling at that time at a rate proportional to 80 degrees, which is the difference. When the cup has cooled to 100 degrees, now the cooling rate is going to be proportional to 30 because the difference between 70 and 100 is 30. So all of these situations can be modeled by this description right here. And that description can be written as a differential equation that looks like this. So the rate of change of a quantity, remember rate of change is given by a derivative, is proportional to, so we multiply it by the quantity itself, which is y here. And so that differential equation we can solve using separation of variables, which I'm going to do here, and get an equation that we can use to model any of those situations. So what I'm going to do here is I'm going to solve this with separation of variables. I'm going to multiply both sides by dt, and I'm going to leave the k over here. I'm also going to divide by y, so we get this with our variables separated. Then we take the antiderivative on both sides, and we get the natural log of the absolute value of y is equal to k times t plus c. Don't forget, when we take the antiderivative, we need that constant of integration. I will point out here at this point that typically y is going to be a positive quantity when we're creating these models. So it wouldn't make sense to talk about a negative population, or it wouldn't make sense to talk about a negative amount of carbon 14. However, in the cooling example, we could be talking about a negative difference where the temperature of something is actually cooler than room temperature and is warming up. And so we do want to allow that quantity to be negative. So we do need the absolute values there. To solve this, we are going to exponentiate both sides. So we get the absolute value of y is equal to e to the kt plus c. Now, we haven't really solved this because we don't really have y by itself because of those absolute values. So we're going to do a little bit of algebraic manipulation here that's going to allow us to get rid of the absolute values. All right, and what I'm going to do here is I'm going to rewrite this expression using a rule for exponents. So if we have e to the a plus b, that's the same thing as e to the a times e to the b. So using that, I'm going to rewrite this as e to the kt times e to the c. And this itself is a constant. I'm going to call it big C. And that constant is going to be a positive value because e to any power is going to be positive. And it makes sense to say that has to be positive because we know y has to be positive. However, if we want to allow y to be negative, what we can do is we can allow this constant to be negative, and that'll take care of the absolute values. So that leads us to the equation y equals c. I'm going to use big C here to replace the e to the c. And then c times e to the kt. And this right here is a general solution to this differential equation. And depending on what we're modeling, we can use initial conditions to get particular solutions and use this to model those situations. Now I'm going to take this another step because what we can do is actually put a meaningful value in here for that constant of integration. So if we think about what's going to happen at some initial time when t equals 0, I'm going to say y naught is the value of y when t equals 0 is equal to big C times e to the k times 0. And k times 0 is 0, e to the 0 is 1, so that gives us y naught equals c. So the value of c is going to be the same as the value of the quantity at t equals 0. So knowing that, I'm going to rewrite this solution as y equals y naught e to the kt. And this y naught here is indicating the value of y at t equals 0. So this general solution right here will always be the solution to this differential equation. Anytime we have a situation that's modeled using this description, the rate of change of a quantity is proportional to the quantity itself. This differential equation applies, and this general solution to that differential equation can be used. And if we know this equation, we don't actually have to do any calculus. Using that equation is just a matter of algebra, plugging in things that we know, solving for things that we don't know. Now, a couple of notes about this. One, the k in either equation, in the differential equation or in the solution, is often called a growth constant or a decay constant, depending on if the quantity is getting bigger or smaller. So if we're looking at a population that is growing, k is going to be a positive value, and it's called a growth constant. If the quantity is decreasing, so for example, radioactive decay, k is going to be negative, which is going to make the quantity decrease as time increases, and it's called a decay constant. Oftentimes, we're going to use something called half-life. So half-life talks about typically with radioactive decay. In a situation like this, it's predictable how long a quantity of some substance like, say, carbon-14 decays into carbon-12, and half of the original carbon-14 exists. So this is an alternative solution that is algebraically equivalent to this. Notice just using a different base here, and then we would get different k values. So this k and this k would be different, but they are algebraically identical. We will not use this equation right here, but when we are doing half-life problems, that equation tends to make more sense. And so you may see that in other contexts, but you won't see that in this class. Also, this exponential model is often very accurate for a certain period of time, but not very accurate indefinitely. So if you think about, say, a population model, let's say we have a population, let's say it's a human population, and it's growing exponentially for some period of time, it's not possible to sustain exponential growth with limited resources. So eventually, the human population is going to grow to the point where we start running out of space, or we start running out of food, or one thing or another, and we cannot sustain exponential growth. And there's another growth model that we're going to talk about that models that, and that's logistic growth. Also, when we're talking about, say, radioactive decay, after a certain period of time, half life doesn't really make sense because we're getting down to the molecular level and counting quantized values of how many molecules are left. And in that situation, then half life doesn't really make sense. So we cannot use exponential growth and decay infinitely long in most situations, but it is a really good model in a lot of situations for some period of